Let's look at a couple of problems about regression, linear regression. This is from Chapter 8 of Bach, Bellman, and DeVoe. These are problems 31 and 33. So we're looking at used cars, specifically used Toyota Corollas in Ithaca, New York. They don't tell us when. Just looking at prices in classified ads, we can figure out the age in the years and the advertised price in dollars. And we want to understand the relationship between those two variables. And so here's the data. Here's the book's version, but you probably can't read that too well. Here's the data. And so the first thing they ask us to do, and the first thing you would always do with this kind of thing, is make a scatter plot. Okay, and that's what I did on the calculator. Now notice you've got to be careful entering this data in. There's multiple data points for most of the years. So I've got like age 1 and age 1 repeated, and then the two prices. And then age 3 is repeated, age 4, etc. Okay, so there's actually 17 cars. The count is 17 here, even though there's not that many rows in the table. Okay, so I named the variables. I put in the data, and then we can go to stat plot. And on stat plot 1, I've already entered in the x is the age and the y is the price. Put it in stat plot mode. The thing's on. Then we could do zoom 9. And whenever you use the zoom, please, 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 look at the window it's giving you and make sure it's reasonable. X is from slightly negative to 14.2. Okay, that gives us a little bit more room than 1 to 13 for the price, and for the age rather. And then the price is from slightly negative to almost $15,000, which gives us some wiggle room on the price. Okay, so right from the scatter plot, we can qualitatively describe the association. Okay, so the association appears definitely negative, and pretty strong linear association. It looks like they are clustering around a straight line, although we could think a little bit about that in a bit once we do a little bit more. Okay, so that looks good. Okay, and part C says, do you think a linear model is appropriate? Well, we already answered that. It appears that a linear model is appropriate from the scatter plot. Okay. Although, as I said, I think we want to say a little bit more about that later. Okay, but they're going to ask us a leading question in that way. Okay, so in the book, they go ahead and give us the r squared is 0.894. Okay, and as a good little exercise in doing a little bit by hand, what is the correlation? Okay, if that's the r squared, what is the correlation r? And of course, despite the fact that one's lowercase and one's uppercase, there's not any difference. So it's going to be plus or minus. Remember, r can be positive or negative, the square root of r squared. Because remember, if you take r, you square it, and then you square root it, you're going to lose the information about the sign. This is this thing that it's very easy to forget, that the square root of a square is actually the absolute value of what you started with. And so to recover what you get, what you started with, you need a plus or minus, and then you need some knowledge of what the sign actually is. Well, in this case, we already know that's going to be negative. There's no way this has a positive r value. So it's negative the square root of 0.894, and that turns out to be minus, well, let's see, let the computer do it. That's going to be minus, and for some reason it doesn't do it on the next line, 0.946, let's say. Okay, so that is a pretty good r value. Now, that's not a guarantee that it's linear, and if we hadn't looked at the scatter plot, we might just be getting very, very lucky on the r value, but it's hard to get that lucky, to be honest. Okay, so that's looking pretty good. Okay, we've got a strong negative correlation value. Okay, and it says explain the meaning of r squared. The r squared value of 0.894 means, remember that the r squared is the amount of variability in the sense of variance, the technical definition of variance, the square of the standard deviation. It means the amount of variability that's explained by, that would be explained by a linear model, which we're going to put up there in a second. Means that about 89% of the variance or variability, let's say, of the price is explained by the best fit linear model, which we're going to graph up in a second. Okay. So that's good. That if you want a simple function, namely a linear function here, that if you plug in, you can predict the prices, and it gives you 89% of the actual variation in the prices. Only 11% is not explained by the model. That's pretty good. Okay. And then the last question they ask is, why doesn't this model explain 100% of the variability? So I just said it's 89% of the variability. Why not 100%? Okay, good sort of real-world reality check question. Well, would we expect that if you just tell me the age of a car, then without any other information, I should be able to perfectly predict the price that somebody wants to ask for it? Absolutely not. There are always other factors. And so the condition of the car, just the whim of the seller, okay, you name it, basically. We can think of other reasons why the price would be higher or lower than the linear model. Okay.